Geometric Series Lesson 1. This lesson will focus on providing and justifying an example of a geometric series, deriving a rule for determining the general term of a geometric sequence, and solving a problem that involves a geometric sequence. In a geometric sequence, the ratio of consecutive terms is constant. The common ratio r can be found by taking any term except the first and dividing that term by the preceding term. So consider a chain letter. 3 people want to start a letter that goes to many. They decide to each send 2 letters to friends requesting they send the letter to 2 friends, and so on. So the first 3 people each send it to 2 people, so there's a total of 6 people then. Those 6 people each send it to 2 people, so they would send it to 12 more. Those 12 people would each send it to 2 people, so there's 24 more. Each successive term is found by multiplying the previous term by a fixed quantity, or in this case 2. Sequences like this are called geometric sequences. Notice our sequence was actually 3 times 2 to the power of 0. So in that first step, that first number, they hadn't sent any letters yet, so it was step 0. The next one works out to 3 times 2 to the power of 1. 2 to the power of 1 is 2. 2 times 3 is 6. The next one works out to 3 times 2 to the power of 2. 2 to the power of 2 is 4, so 4 times 3 is 12. It is the exponent that changes on every successive term. We call the fixed quantity that we're multiplying successive terms by the common ratio, or r. So we can find any term in a geometric sequence with the formula that Tn is equal to T1, the first term, times r, the common ratio, to the exponent of n minus 1, where n is the position or the number of terms to find. So in our example, the 6th term in that sequence we could find by doing T6, which is the 6th term, equals 3, this is our first term, there was 3 people to start with, times 2, this is our common ratio, to the n minus 1. So t to the 6th is equal to 3 times 2 to the power of 5. 2 to the power of 5 is 32, so I have 3 times 32, or 96. So that would be the 6th term in our sequence. So our sequence started off as 3, 6, 12, 24. If we kept going, this would be the 5th term. The 6th term would be 96. Example 1. Determine T1, R, and Tn. Bacteria split in 2. Their sequence of growth is then 1, 2, 4, 8, 16, and so on. If you place 10 bacteria in a dish, they double every hour. Then, how many are there in 12 hours? So in the first hour, there would be 10. In the second hour, it would be twice that much, or 20. Since 10 is what we're starting with, that is our T1. R is the fact that they are doubling, so it is 2. I can find Tn then by substituting into the formula that Tn is equal to T1 times r to the n minus 1. In this case, we want to know how many there are after 12 hours. So n is going to be 12. So then t after 12 hours is going to be equal to T1, which we said was 10, times 2 to the power of 12 minus 1. So this is 10 times 2 to the power of 12 minus 1. Well, 12 minus 1 is 11. 2 to the power of 11 is 2,048. So 10 times 2,048 is 20,480 bacteria after 12 hours. Example 2. Determine a particular term. Sometimes you use a photocopier to create enlargements or reductions. Suppose the actual length of a photograph is 25 centimeters, and the smallest size that a copier can make is 67% of the original. What is the shortest possible length of the photograph after the reductions? So our starting length, or T1, is 25. Our R value is what it's being reduced by. 67% as a decimal is 0.67. And N, our number of terms is actually 6 because there are 5 reductions plus the original, plus 1 original. So our N value is 6. So we can find the size then after those 5 reductions by substituting into the formula that T1 times R to the N minus 1. So Tn is equal to 25 times 0.67 to the 6 minus 1. Plugging into our calculator, we find then that our Tn term is 3.4. In a geometric sequence, the third term is 54. So T3 is 54. And the sixth term, so T6, is negative 1,458. Determine the values of T1 and R and list the first 3 terms in the sequence. So I can write the general term is Tn equals T1 times R to the N minus 1. If I use that fact, I can write that for both of those terms. So T3 we know is 54. So first equation, I know that 54 is going to be equal to whatever T1 is, times I don't know R, but I know that N would be 3. Simplifying that gives me 54 equals T1R squared. This is my first equation. My second equation comes from knowing that the sixth term is negative 1,458. So negative 1,458 is equal to T1 times R to the N minus 1. N for this term is 6, so we have to the 6 minus 1. So the second equation in this problem is that negative 1,458 is equal to T1 R to the power of 5. So I now have 2 equations and 2 unknowns. So this question actually requires me to solve it using systems of equations. I'm going to work with equation number 1 and I'm going to solve or isolate T1. So I end up with T1 is equal to 54. I divide both sides of this equation by R squared. I end up with 54 over R squared. I'm now going to substitute into equation number 2. So equation number 2 is negative 1,458 equals T1, but my T1 is now 54 over R squared times R to the power of 5. Simplifying, negative 1,458 is equal to 54. My R's can be reduced and I'm left with R cubed. Divide both sides by 54 and I have negative 27 equals R cubed. So taking the cube root of both sides, I end up with negative 3 is equal to R. So my common ratio is negative 3. To find my first term, or T1, I can now substitute this value back into what T1 is equal to. So T1 is equal to 54 over R squared. So T1 is equal to 54 over negative 3 squared. So T1 is equal to 54 divided by 9, which is 6. We were asked also to list the first 3 terms. So T1 is my first term. My second term I get by multiplying T1, which was 6, times negative 3. Well, 6 times negative 3 is negative 18. The next term again I get by multiplying by negative 3 is 54, and so on in the sequence. Our last example is an application question. It says a modern piano has 88 keys. The frequency of the notes ranges from AO, the lowest note, at 27.5 hertz, to C8, the highest note on the piano, at 4,186.009 hertz. The frequency of these notes approximate a geometric sequence as you move up the keyboard. Determine the common ratio of the geometric sequence produced from the lowest key to the fourth key. So I know that the first term is 27.5 hertz. I know that between AO and C1, so in those first 4, that N is going to be equal to 4. And I know that the fourth term is equal to 32.7. So my general form is that Tn is equal to T1 times R to the n minus 1. I know that for the fourth term, if I use the fourth term as my Tn, I then have 32.7 equals T1, 27.5, times whatever R is, to the power of n minus 1, so 4 minus 1. This gives me 32.7 equals 27.5 R cubed. Divide both sides by 27.5. Gives me approximately 1.189 equals R cubed. Taking the cube root of that number will give me an R value of approximately 1.06. So that means that my common ratio is about 1.06 hertz. Part B says use the lowest and highest frequencies to verify the common ratio found in Part A. So the lowest frequency, T1, is still 27.5. The highest frequency, there's 88 keys, so it will be T88, is equal to 4,186.009. So I can verify that common ratio in a couple of ways. I'm going to verify it by following the same process that we did in Part A and confirm that we get the same R value. So in Part A, we let Tn be our final point, which was 4,186.009. And I want to show that that is equal to T1, which is 27.5, times R, sorry, I'm having a smartboard issue. Okay, sorry about that. I think we're fixed up now. So times, we have 27.5 times R to the n, which in this case is 88 minus 1. To get R by itself, we can divide both sides by the 27.5. And I'm going to keep all my decimals at this point. Sorry, 27.5. I'm going to keep my decimals because I'm working with approximate values. So I end up with 4,186.009 divided by 27.5 being equal to r to the power of 87. Your calculator will be able to assist you in calculating this. You can do the 87th root of this side, and we end up with 1.06 is approximately equal to r. The other way of doing this is to substitute this value into our Tn equation and solve for Tn. So we would have T1 is 27.5 times r, which we're saying is approximately equal to 1.06. To the n minus 1, n is 88 minus 1. And we should come close to the 4,186. It won't be exact because we've done some rounding in this calculation.